and good afternoon. My name is Uwe Koppe, and I'm in the position of Head of Engineering at the company Microcontrol. And I've been for some quite time the technical director at the Canon Automation, but still are active in lots of these working groups, and I'm still the chairman of the IG CanOpenFD. In my today's speech, I want to share my experience about development of CanOpen devices and creating CanOpen systems. Unluckily for me, most of, let's say, the major points you already heard today. But nonetheless, it's from my point of view, it makes sense that some of the, let's say, major topics you hear 2 or 3 times, so that they are really in your brain and you never forget them, and you don't make the same mistakes I'd made in my company when we were starting up with CanOpenFD. So my agenda for today is, first of all, I want to talk a little bit about the application layer of CanOpenFD, and then we go the top-down approach. We come then next to the data link layer, the physical layer, and of course the end is discussions and questions. And although it seems to me you're a little bit shy today, please, if you have any questions, just ask. That's the reason why we are here today. So let's start with the application layer. So as I said, most of the points, the major topics you heard today, so I keep myself short concerning the application layer of CanOpenFD. So actually these slides are more or less intended for those people who are familiar with CanOpen Classic and need to know what are the changes when we move over from classical CanOpen to CanOpenFD. If you're a newcomer and you just want to start with CanOpen, my recommendation is start directly with CanOpenFD, and you don't have to care about these slides. So what I'm saying here is what are, let's say, the changes that you have to keep in mind when you design a system and you have experience with classical CanOpen and you move over to CanOpenFD. Then it means, if we have a look to the different services, network management means there's no change at all. For network management error control, we don't have any more these nasty node guarding, only heartbeat, which is the good news for the day. Sync, no changes at all. Time, no changes at all. For emergency, you already heard that we have a new structure with this timestamp and new features. So that's the good news again. KDO means we have no RTR support because CanFD supports no RTR anymore. We have now up to 64 bytes of data, which gives us more data throughput, and we have no Boolean values anymore. SDOs don't exist anymore. They have been replaced by this new service called USDO, which is, in fact, if you're a newcomer, a nice service in contrast to the SDO, because this service allows you to have unicast, multicast, and broadcast support. And I'm saying this because still for those which are dealing with classical CanOpen, I often get requests like where people ask me, can't we do these nice features like multicast and broadcast together with the SDOs? My answer is no, that is not the intention, that is not planned. We don't go that way. So if you want to have nice features, jump over to CanOpenFD and use these USDOs. Also, what has already mentioned today is there has been an object dictionary update for CanOpenFD. So here again, a short overview, what is new. So we have a new kind of version information. We have got this active error history and list. We have this routing table, and what is already also briefly mentioned today is we have a new object for maximal available payload site. And this will become important for, let's say, the next couple of months when we're talking about security, because we have to put security somewhere into CanOpenFD. And by the way, for those of you who will try still to stick to classical CanOpen, there will be no fun at all to put security on classical Can and classical CanOpen. So another value another good point to jump over to CanOpenFD. But maybe later on, Olaf will tell you some his thoughts about security on CanOpenFD. But this is already available here, that we have the so-called maximal available payload site. So just in case you want to get into details, the good news or let's say start with the bad news. The bad news is that within the Canon automation, we have roughly 25,000 pages of documentations, of specifications. So the good news is for you, you don't have to read all of them. Here's an overview, or let's say my recommendation, what you should read or briefly review. These are the specifications related to CanOpenFD. And as I already mentioned, they have been, the previous speakers already have mentioned these specifications. So again, have a look at them. The Bible for CanOpenFD is the CiA 1301. So this is your first choice if you want to jump over to CanOpenFD and plan your system design. Let's get into the next topic. We leave the application layer, we jump into the data link layer. And when we jump into the data link layer, the first point is, what is typically your motivation to jump over to CanOpenFD? Well, if I remember my first thoughts, it was data throughput. And what we see here from this slide is, if we just simply compare a classical base frame format, that's the one here in the lower left of this picture, and we have 8 bytes of data, so the maximum at 500 kilobit per second. Then we have at this bit rate, we have a frame length of 222 microseconds. And we get from that having a frame size of 111 bits. And then just for the protocol, I don't calculate here any stuff bits in here, so I just take the net bits. So we have a net data rate here of 288-3 kilobits per second if we're sticking to classical CanOpen. So if we're doing the same bit rate, but now with a larger frame size of 64 byte, we have a throughput of 447.6 kilobit, which is 1.5 times more than with classical base frame format. And just by the way, I'm not using bitrate switching at this time. So just switching over to the CanFD frame gives me more net data throughput. So, and now if we introduce bitrate switching, that leads to the fact that my frame has a total size, a length of 328 microseconds, and I get a net data throughput of roughly about 1.5 megabit, which is more than 5 times the speed of classical base frame format. So this is the major point why people may think data throughput, that's it. And we switch over now to CanFD and make CanOpenFD. But wait a second, just step back to our classical base frame format. So I'm not planning now to talk to you about every bit in this frame format here, but just we want to have a look in this control field with the IDE bit, the FDApp bit, which is reserved at this stage, and the data links field. And if we compare that with the next slide, with the FD frame and the FD frame base frame format, then we see that the control field is different for the FD frames. And that has an impact for your system design. That means FD controllers can read and write classical frames, but not vice versa. So that means for your system design, if you're planning a design with CanFD, that means classical CAN controllers are not allowed in your system. And you can't use them there, because if they see an FD frame format, they will react with error frames. So now the question comes up from you immediately, I guess, oh, maybe there are converters in the market, a kind of gateways which transfer data between classical CAN-open devices and CAN-open FD devices? The answer is no. We had requests for that in the past, but I have to admit, even within the CAN automation, there is no real existing kind of specification how to deal with that, how to map PDOs with only 8 data bytes to PDOs with 64 data bytes and things like that. So if that is your plan to mix up classical CAN-open with CAN-open FD devices, I would say today, from today's point of view, it's a bad idea. So either when you're planning a system, plan it with classical CAN-open, or directly go, everything is working with CAN-open FD, and avoid mixtures of them. There is another point which is nice to mention at this place, and because if we looking right here in the protocol, and which has not been mentioned so far as I remember, it's that bit ESI. That is the abbreviation for error state indicator. And that has been introduced by Bosch for the FD-based frame format in order to tell the system if a node is in error active state or it's in error passive state. And before, in the classical CAN frames, there wasn't such a bit available. So with this feature now, debugging and testing and seeing where something is going wrong, where maybe you have got problems in your topology, where you have got problems with nodes which are in error passive state, you can directly see in the protocol over the bus that there is a node which has a problem, which you have missed the termination resistor, or you have got a long cable stub, or things like that. So these problems where you were dealing with in the past with classical CAN and had problems to find them, CAN-open FD makes it much more easier for your system design and for your debugging of your network. And there's another topic just to mention, and I think already Thorsten Gedenk has also said this bitrate switching is an optional one. So nobody actually forces you to say, I want to use bitrate switching and I want to have higher bit rates. We come later to that topic, why it might be worth of thinking not to use bitrate switching. I'm just saying that because if you open the CiA 13.1 and see there the bit timing tables which are printed there in the specification, you might think that we want to force you to use bitrate switching and to use a higher bitrate in the data phase. But that is not the truth. The point is, if you decided for your system design to just run, for example, 500 kilobit in your system, and you're happy in order to run with that bitrate just to gain higher data throughput because you need more than these old-fashioned 8 bytes, nobody forces you to not to do that. You can run CAN-open FD without using bitrate switching. So now when you do your system design, and when you, especially, I come back also to the presentation of Thorsten Gedenk from Emotas, he already mentioned that also, that what you have to think about is the clocking of your CAN controller and the clocking in your complete system. I'm saying that because there, I will later show the corresponding specifications concerning on that. You can't use any clock rate that you were just thinking of. So in the past, if you were using classical CAN, it was a wise decision to use, let's say, multiple values of 8 megahertz to achieve these recommended bitrate settings that were necessary to use bitrates for classical CAN-open. But with CAN-open FD, and especially with CAN-FD, that changes. CAN-FD requires clock rates of either 20 megahertz, 40 megahertz, or 80 megahertz. Within the CAN automation and within our specification, we recommend to use 40 megahertz. That the major fact of that is we want to make sure that all devices in your network use pretty much the same clock, and that is a recommendation of Bosch. And it's crucial later on for bit timings. Of course, you could use 80 megahertz in your system and then use a prescaler. That's a wise decision, of course. But we have decided to use 40 megahertz because some controllers, like the Cortex M0, don't allow clock rates above 48 megahertz. And so that was the decision internally that we made to use these 40 megahertz clock. Also nice to mention is that some tool manufacturers, I picked it here Peak, but there are others also. They also support for the setting of the CAN-FD clock of their interfaces to select 24, 30, or 60 megahertz. Don't use that. Because if you do so, and you will then have trouble with that your nodes are not reacting on the CAN frames they receive, and you getting error frames on the bus. Don't be astonished. That's the point. Again, use only one single clock rate in your system. Another valuable thing to notice is actually within CAN-FD, no clock values below 20 megahertz are allowed. And what has just recently decided within the CiA working group was that we only allow clock tolerance which is below 0.3% of the clock rate. So only you must make sure that your crystal or whatever you're doing there has only an oscillator tolerance of 0.3%. And of course, if you set up these bit rates then in your system, you must make sure that the prescaler must be the same for arbitration phase and data phase. So that is often, let's say, not known, and people use just some settings there, and they are wondering why the system in the end of the day reacts with error frames and is working not stable. All these recommendations, let's say, lead to certain values. Thorsten Gedenk has also in his presentation already shared a slide with these actual bit timing values. I don't do that again here. What I want to focus on is the topic of different silicons. So also the other speakers have already mentioned these Bosch MCAN, which is from my point of view, let's say the gold standard of CAN-FD controllers. There are other manufacturers which use their own IP core, which are sometimes similar to these gold standards and sometimes not. So I depicted here something from NXP, the RT1170, just to show you that from the register point of view, it's not possible to set up all these value ranges for all these bit timing values in these different segments, for segment 1, segment 2, and synchronization jump with. The impact for you as a system designer or as a device manufacturer is the following, that if you have selected a controller which is, let's say, not according to the gold standard, it might happen that your customer says, I want to have a bit rate of, let's say, 125 kilobit. And if you want to run the system with a 40 megahertz clock, we will later on find out that you can't set up the bit timing registers with the desired prescaler, with the desired bit timing values in that specific controller. So some silicons are really limited. So again, I repeat to what has already been said today here is please be wise in your decision of the silicon that you choose. And there are some more topics to consider. First of all, something which has not mentioned here today is please make sure that your controller that you select really supports ISO CAN-FD and not these. There are still some devices in the world which are sold by silicon manufacturers, which are according to what they say. I remember they are saying a CAN-FD Bosch 1.0 standard and things like that. These are these old-fashioned non-ISO CAN-FD controllers. So don't be surprised if a non-ISO CAN-FD controller doesn't work in your systems. They are still sold, but don't select them. Next point is the limitation number of mailboxes or FIFO support. Again, here, my example is the RT1170 from NXP, which depicts on a data sheet on the third page. We support FIFOs for the CAN. We can have 128 mailboxes. We have everything for CAN. And if you really read the very small letters of the data sheet, then you see there, oh, you want to enable CAN-FD, and you want to run 64 bytes in a CAN-FD message, then you don't have any FIFO support anymore, and the number of mailboxes is limited from 128 to only 7. Surprise, surprise, especially when you already have a running software. For example, for classical CAN-Open, and you just want to port your software to CAN-Open-FD, then you will find out, oh, it doesn't work with that hardware. There are also, as I already mentioned, some limitations on CAN clocking. There are limitations maybe on CAN bitrate settings, and I repeat what already was mentioned today here, avoid external CAN-FD via SPI. That is really a bottleneck. So if your focus in your system for your system design, especially if you want to run a CAN-Open manager, maybe running under Linux, and you hook up a CAN-FD controller via SPI on a CPU which is running on a Linux, and you want to run full speed with CAN-FD, so don't be surprised that you don't get a 100% bus load. It's not available because SPI is a bottleneck for CAN-FD. So again, here the hint for the specifications which are available for CAN-FD especially. We have things like the physical interface implementation, the CAN controller interface spec, system design recommendations. Another nice topic is signal improvement. I come to that later. And not to forget CAN-FD cable. So don't forget the cable if we're talking about CAN-FD. So my last item today is the physical layer, and I love that because I'm an electrical engineer. And typically for CAN, you have this bus structure with a termination resistance at the beginning and at the end of the line. And hopefully then you have, if you look on an oscilloscope depicted here below, you see something like the red line and not this ringing like the yellow line. Because if you have the yellow line, you might have forgotten these termination resistors, or you use long stop lines, or you do some nasty things on the physical layer, which is still a nightmare. And I have to admit, from the Canon automation point of view, we don't have yet a kind of documentation or specification how to deal with different network topologies, but we are working on that. So still with CAN-FD on CAN-Open-FD, the same thing applies as in the past. The bitrate has an impact on the maximum bus length. And if you exceed these values in arbitration rate, this will lead to error frames. You're getting into problems. But especially for CAN-FD, and if you have got higher bit rates, you have something else to consider in your own hardware. It's the so-called secondary sample point, already also mentioned here today. So that means there is a delay on your own node between the transmission line of the CAN and the reception. And your own node must deal with that delay, which is implied by your hardware. And you have to measure them. That means I, as or other companies like which sell protocol stacks and driver software, can't do that for you. We can have a roughly estimated value, but in the end of the day, you have to measure the secondary sample point value on your own and measure that on your own. So still the same applies for the CAN hardware, for the physical interface, like for the like in the past. Make sure that you use a common mode line filter, observe parasitic capacitance, use effectively a pull-up for digital CAN TX pin. If you don't make that, you will have error frames if you power up on your devices. And please measure the delay for your specific hardware and put it in your software. That is individual for every hardware. Now, if you're now running with high bit rates, and if you have got, let's say, a little bit a topology which is not so nice, that might lead to ringing on the bus. And this ringing on the bus is depicted here, and that's a picture which is taken from the CiA specification 601-4. And what you see here from that ringing, what happens is that the receive signal is not, typically we see here these receive signals RxD2 and RxD3, which depict potential behavior which might occur when you have ringing or a longer dominant bit time, which leads in the end of the day to error frames on the bus, and you don't want that. So the way to get around that is our so-called signal improvement capability transceivers. That is, let's say, nothing new as such. They are available on the market, and what they do is they control the impedance when they are switching on and switching off the dominant bit. So in contrast to your transceivers that you know, let's say the old-fashioned transceivers, even the CAN-FD, standard CAN-FD transceivers, they are only active running when they are changing from recessive to dominant level, but these SiC transceivers also do switching, actively switching when they are switching from dominant to recessive level in order to receive a timing, to avoid timing asymmetries between the rising and the falling of the dominant bit. But this, again, of course, has an impact on arbitration bitrate, because it is, as I said, it is actively driving even in recessive level. That means if you think about using a SiC transceiver, then this limits your arbitration bitrate to 500 kilobits, because I mention here 500 kilobit because that is our, within the CAN Open standard, bitrate which is defined. The next possible value would be 800 kilobits, and that is far above the allowable value of these SiC transceivers, which are roughly have a value of 667, 680 kilobits, which could be allowable. So the only thing we could do is limit the arbitration bitrate to 500 kilobit if you want to use CAN-FD and these SiC transceivers. The good news is it's a drop-in replacement. So again, I've got some good news for you. It's a drop-in replacements for these SO8 pinnings, so you can interchange them. But please keep in mind, if you want to design a system which is should be available to run, let's say, at 1 megabit in arbitration bit rate, and also and higher bit rates, and you want to use SiC transceiver, that doesn't work. So it might be also a solution to use two types of hardware, two types of transceivers. We did something like this for some of our customers, just to keep that for you in mind. So here's the result. It's again a picture of the CiA 601-4. If you're using these SiC transceivers, so the impact of the SiC transceivers is really good. And recently we did some tests with long cables, running a system with really long stop lines in our lab, a really poor network design. We tested this with these, let's say, classical CAN transceivers, and it didn't work at all like expected. And when we changed over to SiC transceiver, and it worked perfectly. So it's worth thinking about SiC transceivers, but just keep in mind, again, there are still some limitations. So my summary is, you cannot use CAN Open classic devices in CAN Open FD network when you do a system device. Yeah. Then please think of that bitrate switching is an optional feature. Nobody forces you to do so. whatever you do in your hardware design, in your total system design, use a proper oscillator for the CAN controller. If you don't do so, you're running into problems, and that has a big impact, and it's more important than it was in the past for classical CAN. Review the datasheet of the CAN controller for possible limitations before you start, because if you once selected the wrong way, you don't want to do the development again. And think of maybe using SIG transceivers, but keep in mind that they limit the arbitration bitrate. So thank you for your attendance. Are there any questions?
Maybe a question from my side. So you mentioned the easy bits, and yes, I agree that this allows for diagnostic purposes some use cases and scenarios and solutions. But my question is, do you consider the state of the easy bit also in your CAN OpenFD protocol stack? So
Yes.
in regard of how I trust the data, how I work, or
No,
whether I work with the
no.
data in this way?
It's no, it's nothing like I trust the data. It's more or less designed in that way that we put information like that in our stack as an option in a manufacturer specific object for our devices with the purpose for support and debugging. So as I already mentioned, let's say these features to get information about, let's say, the health of a CAN controller is a feature that we have in our products, in our hardware, I would say for more than 20 years now. But what we always see is when let's say, when you have 20 devices of microcontrol and all their health status is they are sick, then you still have to, and you talk to the customer and the customer says, all your devices are sick, then it's, let's say, quite difficult to find the real reason for the problem. And the trouble is not the software, the trouble is not the microcontroller and any other device of any other manufacturer. The trouble is, from my point of view, 99% is the physical layout of the system. It's the cable lengths, missing termination resistors and things like that. And the ESI bit now allows you to give you more health. Like if you hook up a monitoring tool like from Peak, from Vectors, from others, you can see within the message the state, and you can see within the trace, you can see, let's say, how the health state of devices change. And it's easier now for us, for the support, to trace back even from remote where the problem is. And that is a nice feature for us, which is, let's say, given by Bosch with this ESI bit.